I'll try to understand.
Buenos días a toda la comunidad latinoamericana. Buenos días a todos los científicos, físicos de materia condensada y ciencias no materiales. Esta es la red LAFMAT, Red Latinoamericana de Física de Materia Condensada y Ciencias Materiales. En esta oportunidad vamos a tener la charla del profesor Dulat Daurenbekov del Eurasian National University en Kazajistán. También tenemos la presencia, que nos acompaña el día de hoy también como panelista invitado, el profesor Jumat Kargin, también del Eurasian National University, Universidad Nacional de Eurasia en Kazajistán. Kazakhstan now has a lot of funding from oil, from gas, from mining. So there's a lot of funding who are investing in the science. So they are happy to do collaboration with us, especially Professor Jumat Kargin, who is a powerful professor there in Kazajistán. Profesor Jumat Kargin está feliz también de colaborar con todos los latinoamericanos. Y Kazajistán tiene financiamiento del gas, del petróleo y de las minerías. Y está desarrollando su ciencia. Perfecto. At the end of the talk, maybe you can contact Professor Jumat Kargin and Professor Dulat Daurenbekov para to continue, maybe to try to get links and collaboration with them. They are interested in projects related with these topics, basically, and materials as well. La charla del día de hoy está titulada Luminescent Converters Based on Semiconductor Quantum Dots, given by Professor Dulat Daurenbekov, por el profesor Dulat Daurenbekov de la Universidad Nacional de Eurasia. El profesor Daurenbekov estudió doctorado en física en la Eurasian National University, la Universidad Nacional de Eurasia, y también en el doctorado sándwich en la Universidad de Lomonosov, en Rusia, en Moscú, Rusia. He studied also in Eurasian National University and the Lomonosov University in Moscow, en Russia. Bien, entonces, Dulat Daurenbekov, you are welcome. I introduced you for the people already, and now you can share your screen and you can give your talk for 50 minutes around. At the end, the panelists will ask you questions. Okay, you can share your screen now and you can start your talk now.
Okay, thank you, Luis, for introducing me.
Yes, go ahead. It's ongoing. Yes, we can see. You can share your screen. That's good. Yes, go ahead.
Okay. As I said, Luis, my name Daurenbekov Dulat, surname Daurenbekov, name Dulat. Actually, I'm not a full professor. I'm acting associate professor. And I want to present my research topic, luminescent convert based on semiconductor quantum dots. The relevance of the research, as you know, there is some problem with the energy and in our world that we need to increase our solar, increase power, energy. We need more energy during the time, and that's why we want to study the solar cells, because the solar cells we can produce the energy from the sun, and as we know, there's a lot of laboratory, a lot of studies in the solar cells field, where researchers tries to increase the efficiency. The main idea how we can increase the efficiency and produce semiconductor solar cells by heterojunction structure, It means that we can put a lot of different semiconductors materials like a sandwich and obtaining the getter structures, and by this process we can increasing the efficiency of solar cells. From the top of the solar cells we put the wide bandgap semiconductors, and going to the bottom it will be in decrease in the bandgap, and that's why we can increase this efficiency. But we take another way. We decide to increase this solar cells efficiency not by changing their structure, not creating new solar cells. We just take commercial silicon solar cells with their average efficiency, and we try to increase their efficiency. For example, as you know, maybe about 70% of ultraviolet solar and visible solar radiation goes to the heating of solar cells, and only 30% of the radiation goes to the generated electricity, because silicon solar cells has a band gap near the infrared region, and that's why the power, the energy, high energy of ultraviolet, it's too powerful. It's a lot of energy. That's why majority part of this energy goes to the heating by relaxation process, or goes to the phonon. Uh, and we tries to solve this problem, and we tries to convert this 70% of energy comes from the sun to infrared region, where the solar cells have the good response for solar radiation in the red region. We That's why we try to obtain material, maybe new material, which involves luminescence properties and down conversions. It means we convert from the high energy to low energy, to down energy, from solar spectrum. Okay. In this case, we use luminescence coating process based on the cadmium selenide core shell and cadmium telluride quantum dots. Okay. The goal of investigation is investigate the intrinsic and impurity luminescence of quantum dots, because you know that a lot of materials as a host can exhibit their own intrinsic luminescence. But if we add the impurity, we can increase or their luminescence properties, improve their luminescence properties. That's why we study intrinsic and next impurity luminescence of quantum dots like cadmium selenide, cadmium telluride, cadmium selenide doped by Cooper, and core shell quantum dots. Okay, and the research topics, it's my objects. It's the same semiconductors. Okay, next slide. I just want to show you what kind of equipment I use. As in general, what I did, it's a installation synthesis of quantum dots. It's like we obtain in the final, we obtain the colloidal quantum dots by this scheme. This heating, this is glass, and the heating temperature about 130 to 250 degree, and its process goes in the argon atmosphere. Okay, there's a ocean optic spectrometer. It's for in situ spectroscopic. As you know, we can obtain the process of synthesis in the online. Online, it means in that time when when quantum dots obtaining, we can see their luminescence by exciting and detecting the luminescence. Okay, it's like a microscopic study. Here, Sam and Tim, there is a solar simulator where we study our solar cells coated by the luminescence material. Here is a how you say it? It's a spectrophotometers, the spin coating equipment. Okay, the main goals of our study, it's investigate the emission, excitation spectrum, kinetic by in situ method, size dependent luminescence, because as you know, the quantum dots have size dependent properties like luminescence. If we change the size, we change the band gap. That's why we change luminescence. We can move it, shift it to the different area. Then we study. Then we try to dope cadmium selenide by Cooper, because Cooper usually uh, have their luminescence in the red area, and by doping the cadmium selenide, we can increase the luminescence in the red spectra. Next, we study the quantum dots by their quantum yield, because uh, depends of quality of your quantum dots, depends of what kind of core shell you use. If they got zinc, sulfur, and other maybe cadmium sulfur system, depending of the how you grows their shell, its influence depends for efficiency, quantum efficiency of these quantum dots. And there we tries to use cadmium selenide, core shell system in the some polymer. We add polymer and obtaining the luminescence coating layer, and we coating this layer on the industrial or commercial solar cells, and trying to increase the efficiency. Okay, first of all, by using in situ method, we put in laser in the solution and excite this solution by ultraviolet, like 400 nanometers, and another laser, another оптоволокно, да, как это? Оптоволокно we use for registration process. And by excitation, we can see, under excitation and during the temperature increase, we can see how their shift happens. It's like shifting the luminescence because of the size of quantum dots increasing, and that's why the luminescence move to the long wavelengths region. More, you can read here, the shift of luminescence band is associated with the formation of particles of different sizes. Band gap decreases with increasing quantum dots, and we can see it on the figure. It's for cadmium selenide quantum dots. Okay, next slide. Here is the transmission electron microscope images. You can see there's size of quantum dots. Here is their diameter. Here's their band. It's their absorption spectrum basically. And by this, we use their um, empirical equations. Oh, we can use empirical equations for calculating the size of quantum dots. But another way, we by absorption spectra, we put the wavelengths of absorption spectra for this empirical equation and can calculate their size here. But another way, we can just use a transmission electron microscope and just using the program and calculate the distribution of the size of quantum dots. Here is their distributions. As you can see, and the 170-degree, the average diameter of the quantum dots 3.3, and by increasing the temperature, you see how increasing the size of quantum dots, and also their shift in their luminescence. And in addition, we used some different approach, like a single addition of top selenide. It's a precursor of selenide. The top it's a trialkylphosphine, and selenide it's a precursor. We just use different variations for adding the precursors in to the solution. Okay, next slide. Here's in exactly in situ measurements. Each dot is a measurement, and you can put your different time. For example, each 10 seconds, each 20 or 1 minutes. After 1 minute, it measure the position of the luminescence. It's like this, but there's a final result. But here how it starts from the 0 second point and how it goes. And of course, there is some an additional shift, because we measure this in the at the high temperature. As you can see, there at this point, at the 0 point, we add the top selenide precursor. It's a second precursor, and you can see how luminescence start to move into the long wave range, or to the red range of spectrum, and you can see it's like a lined straight line here from and in this moment all precursors are used in the reaction, and the reaction almost stops because all quantum dots are created, and all chemical reagents spent for these quantum dots. And if we how say approximate for 500 seconds, nothing change. For this temperature, for this chemical reagents concentration, there is a final stage of the size distribution. And here is the absorption spectra of the final obtained quantum dots at the different temperature. As you can see, their band gap moving to the red spectrum. This is from 117, red 119, and to the 217. It's almost 700 nanometers. And here is empirical equations, where we can put the lambda nanometers here, and here, and calculate the diameter. And here is this calculation. Okay, by in situ measurements, we investigate the gross kinetic cadmium-7 and cadmium-2 quantum dots in the wide temperature range, because temperature is the main parameter which influence for their size distribution, and where you can see their luminescence. It's the main parameter of their temperature, and we studied it. And now we exactly know in which temperature and for which quantum dots it's characterized with a constant, of course, concentration. Next, okay. Next step, as I said, we tries to use some impurities like copper for cadmium selenide. As you can see here, not here. Here's cadmium selenide. It's like from 550, 60 to 700 nanometers. But okay, and we tries to add some impurities to increase the luminescence properties in the red area, red infrared area. Here is luminescence of quantum dots. It's about 625 nanometers. This big straight line, it's excitation laser, because we measure it in the in situ and the solution, and some signal from excitation source comes to the detector, and that's why we can see there's a peak, big peak. But this peak, it's quantum dots. Okay, at this point we add the copper precursor or copper impurities, and you can see like what process happens, that host luminescence or band gap general luminescence decreasing, start to decrease, and in this time the impurity luminescence increases. Host luminescence decreases and luminescence impurity luminescence increases. You can clearly see it on the figure, and this is point the last one measurements at 180 seconds, and the majority part of the luminescence comes to the impurity. It's for 1% of impurity. Okay, here is study the excitation spectra of quantum dots, cadmium selenide copper, by as you can see, the luminescence of impurity luminescence and the host luminescence matrix intrinsic luminescence have the same excitation spectra. By that, we can say that impurities are introduced inside the host of luminescence, and this direct excitation, and host gives the energy transfer from the host to the impurities. Here and then we measure the efficiency in the long range, in the infrared spectra, and for different percent of precursors. For example, for 1% it's 10.2, and the biggest it's for 10% of copper, it's 12.7%. Do you hear me? It's okay? Everything is okay?
Yeah.
Yeah, we can hear
okay,
you.
okay.
Go ahead. Go ahead.
Okay. Here's the luminescence of impurities. Here's the luminescence of quantum dots, their host, and that's all. Okay, and the inset, there is a luminescence after the Mars. We can see that luminescence of the impurity part disappeared. We see it on this in the sample. As I said, our sample was in the solution, and we see that in the solution on the bottom of the glass some dark points. It's like all impurities go out from the host of the quantum dots, and they precipitate it under the bottom on the glass. That's why we conclude that all impurities, how you say it, catched on the surface of the quantum dots, not inside in quantum dots. Okay, here's like a schematic illustration how we see the energy transfer from the host lattice to the copper impurities. It's a conduction band, it's a valence band. When we excite the electron from the valence band to the conduction band, there is some recombination process, of course. And it's a recombination process we can observe like and here. It's a 0.580 nanometers. But another one is related this luminescence related to the impurities defects. As you know, the quantum dots, they are very small, about 2 or 10 nanometers. That's why impurities, it's very difficult to goes inside the quantum dots because their surface states it's more powerful in this case in case of quantum dots, and that's why all impurities tries to catch on the surface area, and it's like not always they incorporated in the lattice of the quantum dots. Usually they're like a defects. It means like, and that's why the defects influence to the main energy transfer by decreasing the energy like this. Okay, next step, as I said, we want to use our quantum dots as a films, as a coating material for solar cells. Here is a schematic illustration. The optical diffusion reflection of solar cells. It's a first line, a blue line, and the second line, it's a solar radiation. As you can see, the majority part here okay. This energy efficiently absorbed by the solar cells, but as you see, it's a big energy, and a lot of energy goes to their heating. And as you know, there is some process, a lot of process like energy, like heating, heat moving, charge carriers, or not divided in their positions. They can recombine with a negative effect for solar cells, and only this part this part have a good response, better response, and enough response for creating electricity. And we try, like by this arrow, we try to how say downshift our solar radiation to the infrared spectrum. Okay, for this case, we studied the core shell system. We understand that only if we put only quantum dots, cadmium selenide, for example, it's not enough because their efficiency is very low. As I said, their surface states have a bigger influence for quantum dots. That's why a lot of surface defects like vacancies and other defects, a lot of dangling bonds. They're like traps for electrons and holes. That's why we should create a core shell system. A core shell system passivates the surface states. And usually for core shell system, if you want to increase our efficiency, we should use a bigger band gap than the host. The shell should be bigger. For example, if for cadmium selenide it's about 3 how say electron volt, for zinc sulfide sulfur it's about 4.5 electron volt, like this. And here is their efficient quantum yield luminescence we measured depending of how much shell we should create for quantum dots. Here is the efficiency, and for example for 1.4 relation with cadmium and zinc, it's a bigger efficiency, 32.8%. Okay, and you can see these differences. Okay, next. And this is a schematic illustration how we use our polymer system with the quantum dots. At a polymethyl methacrylate, it's a standard, maybe you know, polymers. It's like glass. We usually see it in our life. It's okay, and we put a quantum dots. Polymethyl A, we solved. We put in the chloroform, and quantum dots can solve in chloroform, and we mixed this system together and put it on there's a solar cell. We put this on the surface of solar cells by dropping, and by spin coating this, we obtaining this system solar cells on the top surface polymer plus quantum dots. Here's a schematic illustration. Light luminescence downshifting layer. Here is white, and this is imaginary quantum dots. And by excitation by solar radiation, you can see an addition radiation comes to the solar cells model. Okay, here's what we measure. How we measure efficiency. As I said previously, we have a solar simulator which simulates the spectra of solar radiation on the surface of Earth, and we just measure solar cells without coating. It shows our 17% efficiency, and when we put the first layer, it's about 150 micrometers, and we can see there's some increasing in the efficiency, but not enough. And we put the second layer, it's increasing efficiency to 22%. I didn't add the others because I didn't add all information, but I can say that if we put the third layer, or there's decreasing in the efficiency. Maybe if you ask me, I can say why. Okay, this is schematic illustration at the original solar cells. It's the first line here is the dark line, and the second one it's with one layer. It's very close, and that's why it's difficult to figure out it. But when we add the second two layer, sorry, and this good increasing in the solar cells. And there's the solar cells diffusion reflection spectra. So you can see that there's a good absorption process happens here. That's why it's a good absorb the solar radiation. Okay, next. Then we put the quantum cadmium telluride quantum dots, and there is the same increase, but as I said, the cadmium telluride quantum dots, they have their smaller band gap. There's not correct efficiency if it's for cadmium selenide core shell, but as because of the lower band gap, their luminescence in the they shifted to the infrared about 800 nanometers, 8.809 50 nanometers. And at the same process, we add we just understand how it goes, and we put the first layer, second layer, but we know that the second layer is more efficiently, and there is some increase in about 60% increasing in the solar cells. Okay, in conclusion, we studied growth kinetic by in situ method. We understand how growth, how obtain the quantum dots with the characteristic peak luminescence in the exactly temperature, and we know the size distribution by synthesis, and in the final we add the goodest samples for LDS layer at luminescent downshifting layers. We use these systems: cadmium selenide zinc sulfur plus polymer and cadmium telluride plus polymer, and as you can see in the figure, the efficiency of solar cells goes to the 5-6% increases compared to the original sample. Okay, thank you for attention.
Thank you.
Thank you, Dulat. Very interesting talk. Very interesting talk. Thank you. Now we are going to start with a question from the. We are going to start with a panelist. Okay, we have many invited panelists because this topic is very interesting. Let me introduce us. Let us welcome Professor Efraín Viesca Villanueva from the University of Coahuila in Mexico. Damos la bienvenida ahora al panelista, al profesor Efraín Viesca Villanueva de la Universidad de Coahuila, México. Efraín, you can start with your questions, please. Efraín.
Thank you. Any question?
Can you open your camera, please, in order to the people can know you? Okay, go ahead, Efraín, with your question to Dulat. Efraín, your microphone. Can you ask your question, please? ¿Puedes hacer tus preguntas, Efraín? Tu micrófono.
Thank you. Any question?
You don't have questions. Okay. So, okay. Well, welcome anyway. Welcome anyway. Bien. Now we are going to continue with another invited panelist, which always is with us every Saturday from the University of Cambridge and also the University College of London, Professor Stuart Holmes. Stuart?
No.
Thank you, Dulat, for your talk. Very interesting. I have a few questions. First of all, I didn't quite understand what was the role of the copper. The copper makes a defect level and can charge up. Is the exciton trapped in the defect and somehow changes the efficiency? What is the role of the copper?
Okay. Thank you for the questions, Stuart Holmes. The role of the copper, we just try to give an addition redshift for our quantum dots. Because our quantum dots, for example, cadmium selenide, they have the luminescence about the maximum region which we comes. It's 700, like 650 nanometers. But by adding the copper impurities, we can additionally create the impurity luminescence, impurity associated luminescence, basically, and it's in range of 850 nanometers. It's the main role, but as we understand, this impurity it's very different to incorporate the quantum dots. Okay, we incorporate, but their main position on the surface. That's why it plays a role like a defect. Defects not incorporate inside the host of the structure. And after the 1 week or 2 weeks becomes decreasing of this impurity associated luminescence because how it's difficult to catch on the surface.
Perhaps for an application, you would have to overcome that problem. Maybe.
Yes. Yes.
Yeah. The other question I have is, when you coat the solar cell, you seem to get an increase in the open circuit voltage. Is that a real effect? That's quite interesting.
Yes, it's
the current voltage characteristic, and the open circuit voltage shifts to higher value, meaning you have a higher overall efficiency.
Yeah, yes, it's we measured on our equipment. It's a solar cell simulator. It's we put the context, we put the coatings. It's all the relevant results. But the main problem with these results is it's during. It's not how say after sometimes the properties of such process increasing is negotiated. How you say it? It's because it's all organics.
Yeah.
There's some chemical reaction inside this.
Yeah. So it's so-called short-lived, maybe.
Yes.
Yeah. It's very interesting talk. Thank you. But I'll stop my questions there. But thank you again.
Okay. Thank you for the questions.
Thank you very much, Stuart Holmes from the University College of London. Now, at the University of Cambridge, now we are going to move to Latin America. Let's go to Chile first. Chile, with Professor Sergio Conejeros Espindola, the Northern Catholic University of Chile.
Okay, hi. Thank you very much for your talk, Dulat. Very interesting work. I have just a few questions about, for instance, have you tried to incorporate rare earth elements or cations like europium, or samarium, or because these elements are very well known for the luminescence properties. So have you tried those elements, or you are not really interested on working on this kind of rare earth elements?
Thank you for the question, Sergio Senejeros. Yes, we tried add some rare earth ions elements like europium, like terbium, niobi, samari, but it's very difficult to incorporate in the quantum dots. Okay, you first problem when you add some precursor like with rare earth ion, basically this precursor have a luminescence. When you add in this precursor to your quantum dots, and there we don't clearly understand if it's incorporated inside the quantum dots or it in the solution, because part of the precursors not always reacts with quantum dots, and when you looking for the luminescence, you can observe the luminescence of europium, but it's not the luminescence from the quantum dots, and it's not luminescence from the europium inside the quantum dots. It can be luminescence from the just europium precursor. It's very difficult to clear. Okay, we use how say how we clean our samples in the chemical solutions, and we clean it by the centrifugation, and the part of the quantum dots with a high big mass precipitated on the bottom, but some part of the precursors of europium can precipitate it too. But it's one problem. The second one problem, okay, for with Europeans this problem, but another problem with for example niobe and other lanthanoids where infrared spectra, it's very difficult to registrate the luminescence because the infrared spectra was very difficult for us. But we obtained the luminescence of europium, terbium, but we didn't clearly understand what kind of luminescence it was, like this. But it was for zinc selenide, not for cadmium selenide.
Okay, thank you. I have another question with respect to the copper incorporation as dopant in the matrix structure, in the host structure. So I would like to know, because you told to Professor Stuart Holmes that is the incorporation is like a defect. It's not substitutional, right? I mean the incorporation is in the intertidal sites, right? Not in the
Yes. In general, it's look like this. Not like in for in place of ion of cadmium.
Yeah, but that is because of the synthesis method that you are using, right? Because you are just using a spin coating for doing this kind of for instance,
No,
if you
for
use
incorporation copper, we use a chemical reaction in the glass in the about in temperature about 200 Celsius degree. The quantum dots at the process of impurity process, adding impurity, it their how say, I forget. Джумат, может, подскажете, растут. Growth. Their growth of quantum dots and growth, and when we put the impurities, they growing together. And in this time, in this moment, the impurities introduced inside the quantum dots.
Okay. So the last question: have you tried to run some computational calculation for understanding your experimental results, or for having a match or a deeper understanding of the experimental work?
I don't clearly understand the.
Have you performed a computational studies like a DFT
compositional.
calculations? Yes, for having a deeper understanding of your experimental results, or some collaborations with people.
Okay, we did some compositional studies like ICP-MS, but it's only for quantum dots. We just know the stoichiometric structure, and okay, we have these results. But for the final results for increasing the efficiency of solar cells, they're not have so big influence. In general, we understand the stoichiometric. We just want to write. We just want to exactly know, but we have these results like a ACP-MS. It's general method for understanding there. And another method is EDX analysis. It's from Tema, transmitted electron microscope. We obtain the same results, the composition of quantum dots, because the
Okay.
composition have some difference in depends on the synthesis. Okay, thank you.
Okay, thank you again for your very nice talk. Okay, thank you. Bye.
Thank you too.
Thank you, Sergio Jonejeros. Dulat, I think Sergio was asking about the theory.
Theory? No,
theory? Not
no,
a theory.
no theory, only experiment.
Okay, maybe you can get some connection with Sergio Conejeros. He's a specialist in theory.
It's like DFT, maybe that like this.
Yes.
Quantum calculations.
There is also another specialist from Chile who also studies DFT and so on of those kind of systems. It's in the south of Chile, in Puerto Montt, who is Professor Felipe Mundaca from the University of San Sebastián in Puerto Montt, Chile. Felipe.
Hi, how are you? Thanks for your lecture. Well, I have one question. When we prepare a quantum dot for solar cell, the interest is convert ultraviolet energy in solar energy, no?
Yes.
In addition, the intention is to reduce the heating of the solar cells. And in your experimental result or in your investigation, you measure this or you avoid this heating in the solar cell by your quantum dot?
Yes, our equipment, like the solar simulator, have this function, like heating the sample on the holder. But the maximum temperature of the heating about 50 degree. We measured this, and as all solar cells, the efficiency start decreasing after the heating. Yes, it happens the same. This happens and with our samples, but I didn't show this in the presentation.
Okay, and another question, and I don't remember in the page 10 or 11 when you intend to explain the mechanism of the photoluminescence. You shown us the energy band of the impurity of copper. The copper were in the surface according to your picture. How do you know that? By other experimental result or computational result?
How we know that on the surface, Cooper?
Yeah.
It's like how you say it. It's from the general theoretic maybe understanding how quantum dots their properties of quantum dots, because as you imagine quantum dots, it's like a very little particle, about 2 nanometers maybe in the size, and if there are some defects are created in the, for example, we know that no ideal crystal structure, there are some defects should be, but all defects in these systems goes to the surface, because in the surface the defects level is more comfortable with the lower energy. That's why the Cooper should goes to this side, and like this all defects should go to the surface states, because by the lower the energy, like vacancies, like other defects, and Cooper the same. But we didn't measure experimentally this. I just don't know how it measure.
Okay. Thanks for again.
Thank you to Felipe Mondaca.
Thank you, Professor Felipe Mundaca from Puerto Montt, Chile. Now, let's move to Mexico with Professor Arturo Martinez, Sinvestap of Mexico. Arturo? Your microphone, Arturo. No, it's not working. Maybe you can type and then we can read later on. Okay. While we're waiting for the question from Arturo Martinez. Okay, Arturo Martinez sent the question, says, what kind of solar cell do you use for your experiment?
We use silicon solar cells. It's a polycrystalline silicon solar cells. It's commercial. We have a factory in our city which produce solar cells, but major part comes from the China, but some part we producing some part of production in our city, and we buy this solar cells and did some experiments. It's a silicon polycrystalline solar cells.
Okay, thank you for the answer to the question. Well, let's see if from Venezuela there are some questions. Maybe Jose Fermin, you have questions, or the Venezuelan public has questions?
Yes. Hi, Dulat. Thank you for your presence here. Join us this Saturday. I have noticed that you have measures within the range from 170 degrees to 270. Yes?
Yes.
Have you tried to measure your cells at temperatures closer to room temperature?
We measure in situ. In situ measurements was at 170 to 170 degree. Yes, and okay, it's we try to understand how kinetic growth are happening by in situ method. But then it's called to the room temperature. We precipitate our samples and measuring on the stationary spectrometers, the absorption and luminescence spectra. All measurements next happens in the room temperature.
Okay. And last question: how can you, with respect to copper, I suppose you deposit a layer, a very thin layer of copper. How can you avoid the oxidation? Because you know that at those levels in size, copper is oxidizes. So experimentally, how do you avoid oxidation of copper?
Okay. When we add impurity, copper impurity or precursor impurity to the solution, there inside this glass, three-neck glass, there is a argon atmosphere by the argon atmosphere, and that's why there is oxidation. Okay, it happens. It could happen oxidation, but not majority part.
Okay, because you're working in high vacuum. Okay.
Okay, oh, so there is no high vacuum in the pressure of argon atmosphere.
Okay. Okay, that's all for me today. Thank you, Dulat.
Okay. Thank you, Joseph Fermin.
Thank you, Professor. Thank you, Professor José Fermín from the University of
José.
Zulia, Venezuela.
Gracias.
Well,
Please. Thank you, Luis.
Let's move to Colombia. Maybe there are some questions from Colombia or from the public. Ximena, are questions from the Colombian colleagues or from the public?
Good morning. No, you don't have here. We don't have questions from our university. Only the people said that thank you for the talk and the interesting topic about this.
Okay. Thank you, Ximena. I think that there are some people from Kazakhstan. There is one Mikhail Kroitoru. Mikhail Kroitoru.
Good afternoon, probably, or good morning. Yes.
Your camera, please.
Mikhail Kroitoru from University of Recife, Brazil.
Brazil. Okay. Because the name. Okay.
Yes.
Maybe
But,
thank
you for the talk. Thank you for the interesting topic and interesting talk. The question is probably it's beyond the talk, but maybe you have some intuitive ideas. If you can control. So again, the question about the impurities, copper impurities. Have you during your measurement and during the growth, maybe you have observed what, and you have an idea what kind of distribution of those impurities you can see there, or if you can see them, and how the statistics of this distribution can influence your results. So the question not about the amount of impurities, but about the distribution. And maybe this distribution of impurities can be controlled by the temperature you use for growing your samples.
The last words I didn't understand. What control you said?
If you can control during the growth process of your samples, if you can control the distribution of the impurities, the distribution of copper impurities in your samples. Of course, the sample is quite small, but maybe you've observed some unusual behavior in the measure during the measurements. And if this unusual behavior is related to the distribution, how they are distributed in the samples, and if you can control this distribution by temperature you use for your growing process.
Okay, thank you for the questions. It's a chemical methods. It's very difficult to control the impurity distributions. If it was a physical, some methods, some epitaxial, some evaporation, some magnetronic, it's possible, but in the chemical reaction, it's very difficult to control the distribution impurities inside the sample. But the general methods which we use how to control maybe a distribution. For example, we can add some core shell system, which by core shell system we can hold our impurities inside the quantum dots by core shell. And another one methods is fast cooling the chemical reaction, stopping. For example, if you stops your chemical reaction very fast by adding maybe nitrogen, liquid nitrogen, it maybe can give better distribution of impurities in the sample, but we didn't try it. But we just put it on the water, our silicon glass, tuna glass. But if we add nitrogen liquid, it will be some different distributions. Okay, but we measured EDX from the Tema analysis, and by measuring this results, we figure out that impurities is like spread on all samples, and impurities in addition inside the solution. Not all impurities inside the quantum dots.
I see. Thank you. Thank you
Thank
for
you
the
for the
talk.
question. Thank you for the question, Mikhail.
Thank you, Mikhail. I'm sorry that because the name Mikhail Kroitoru, we believe that you are from Russia or from Kazakhstan because the name.
Yes, indeed. Yeah. So name is Russian, family name is Moldavian, Romanian, but I'm affiliated currently also with Brazilian University.
From Brazil. Well, let's continue to Brazil with Professor Isaías Gonzaga Oliveira from the Federal Rural University of Rio de Janeiro.
I don't speak Russian. I'm not from Romania. Just a joke. Thank you very much, Dulat, for your very interesting talk. I don't have any question, but I'm very happy for learning good things in your work. Thank you very much.
Thank you.
Thank you, Isaías. Thank you.
Isaías.
You can mute. Okay. Well, now we are going to invite Professor Jumat Kargin from the Eurasian National University, Kazakhstan. You know that Kazakhstan nowadays is growing very fast economically because they have a lot of gas, oil, and also mining. And I think that Professor Jumat Kargin, you can comment something, or you can invite people to collaborate or something from the Kazakhstan team.
Okay, thank you very much, dear my friend Luis. So, and I want to add one sentence to what to your previous comments. We also have a lot of friends from different parts of our world, and today this workout is some of the confirmation of that. So, and first of all, I'd like to say big thanks to all people who is joined to us today. Especially thanks to Professor Luis de los Santos Valadares for arranging this meeting. So it's very amazing because I cannot say just we every day meet different people from different parts of our world. So, and today we understand that it's indeed our world's not so big because via internet, via which how it's called this browser, we can meet with each other. So, and about this title of today seminar, today workout, I'd like to say thanks to my colleague Dulat. I want to say that Dulat, one of the young scientists of our university, you know that Eurasian National University, one of the how can I say, one of the biggest universities in our country. So, and I'm happy to work with very smart people like Dulat. I believe that young generation who is represented Dulat for us is they have a good opportunity if you will compare with us to take the big achievements in science in every field. So and especially for this for seminar, this title, Dulat, my question is, what you say? As you said today, that this is experimental work, but you know, for our country today, no, for just only our country, it's the big advantage for different countries, the process of commercialization, the scientific results, it's one of the big advantages. So what you say, how we can use in practical goals, in practical your results?
Okay,
because you everyone understand for today for industry solar who is manufactured solar cells, the biggest profit is just only 14-15%. Yes. And just in laboratory, we can read that this scientific team or another team find out they achieved approximately 40% of profit. But what you say? Thank you.
Thank you for the question, Jumat Kargin. Practical application, yes, we can use it for practical application, of course, but there are some problems. Firstly, we should solve the first one problem is some degradation during the time. This coating, luminescence coating, degrade during the time, and the all increasing efficiency becomes neglected after the time period because it's a polymer, our quantum dots, it's a chemical solution. During the time the chemical reaction happens inside this material, and there is no increase in efficiency at the first step. And the second problem, we should find more suitable polymer system, because it's we should know how works polymers, how quantum dots react with this polymer. Okay, this main two problem. And it's a third problem, it's increasing the efficiency of quantum dots, because it's okay, these three approaches, it's very difficult to do. And okay, so if you can solve this problem, we can move forward. But as I know, your questions inside, that we can win some grants, some projects, and do some experiments. But okay, we can write project, we can win project, but we couldn't write this good article because it's all how say only practical. It's just a practical study. It's very difficult to write some article because we need to publish 2 articles as a result of our project, like this.
Okay, thank you very much. I just wanted to wish you to take in the future good results, and maybe your results finally to lead us to the biggest advantages in this area. So,
Okay, thank you.
by the way, for our government policy in the according to our government policy in this renewable energy, because for us it's one of the biggest how can I say is one of the crucial trends for our country, because you understand that the mineral resource like coal, oil, gas, it finally in the future it can be finished. So, and we should today to think and to support like this investigation. And maybe you know another of our goals in international goals is to increase the part of the renewable energy like solar, wind energy, and so on. The part increase from 5% today to 15% to 2030. So, and
Yes,
I hope, I believe that this investigation to finally will be the one of the steps to our moving in this ways. Thank you.
Okay, thank you very much, Professor Yumar Kargin from the Eurasian National University, Yumar, and Dulat. Professor Albino Aguiar from Recife, from the Federal University of Pernambuco, wants to participate and comment as well. Albino?
Thank you, Luis. Thank you, Professor Dulat, for the very nice and interesting presentation. I have two questions. One is back with the copper addition. Professor Mihail asked about the distribution. And my question is about what happened with the quantum efficiency if you increase the amount of copper. There is I imagine that there is a limit for the copper addition.
Thank you for the question. Okay. The addition of the some amount of impurities, some saturation process happens after the 10% of adding concentration. We calculate it by mole. Of course, not all 10% impurities incorporate inside the quantum dots. We can control what we add. We can control what can incorporate inside by increasing concentration of adding impurities. After 10%, it becomes saturations. It's like concentration quenching happens inside the impurities luminescence. It decreasing, start decrease.
Okay, thank you. What is the limit of the quantum efficiency? There is a theoretical model for limit, as Professor Schumann mentioned, in commercial solar cell efficiency is quite low, around 15%, 12 to 15%. In laboratory, efficiency reach even more than 40%. How can we approach these limits from laboratory scale to industrial scale? Do you have an idea?
usually, my idea is like we can approach the the laboratory scale results like with 40 or 45. I know experimental results in laboratory with the solar cells. It's a heterojunction solar cells which consists of more than 10 different materials like gallium arsenide, cadmium telluride, zinc selenide, and so on, copper oxide. There's a lot of materials which can be created as a heterostructure, but as you know, all components are expensive, and the procedure of this create this solar cells is very difficult, and that's why it's so expensive. It's but our approach is cheap. We just use solar cells, commercial silicon solar cells, polycrystalline. It's very cheap, and we just increasing the efficiency by 5, 3, 4, 5, 6% by adding. We don't interrupt the production process. We didn't change nothing in the production process. For example, we just add a final one only step. There's putting some coating layer on the surface. But I know there's some new third type of solar cells. It's perovskite solar cells. Maybe some how to say it, future for these solar cells. What can I say?
Thank you again, Professor Dulat, for your talk, and thank you for your answer. And I wish you good work in improvement in your work. Thank you again. Thank you, Luis.
Thank you, too.
Thank you. Thank you, Albino. Well, Dulat, let me mention very quickly the next talk for the public for the next next weeks, please. Next week, 20th of May, the talk will be from Dr. Alifers Mestra. The talk is condensador híbrido asimétrico en 3D basado en copper 3, oxygen 4, cadmium oxide carbonate, carbon activate carbon, y sobre sustrato de espuma de níquel. The professor is from the Universidad Católica del Norte, Northern Catholic University in Chile, and the moderator will be Sergio Conejeros. It's on May 20. On May 27 will be Professor Edson Sardella from Brazil, and the moderator will be Professor Isaías Gonzaga Oliveira. On June 3rd, Saturday, June 3rd, Professor Diego Lamas is going to invite one speaker who is going to confirm. On June 10th, Professor Stuart Holmes is inviting another speaker. He's going to give us the talk soon, or the information, all the details soon about the speaker on June 10th. On June 17th, the talk will be related to materials for artificial intelligence, materiales para inteligencia artificial, who is Professor José Fermín from Venezuela, is inviting one speaker. Well, those are the talks for next weeks. You are invited as well to participate whenever you want. Okay, you can join us whenever you want. And Dulat, thank you very much for your talk. Any words for saying goodbye to everybody, or you want to say something to Adi?
Okay. First of all, thank you, Luis, for inviting for such a seminar. Thank you all for the questions. I appreciate that you was interested in my speak. And Luis, in addition, congratulations on your wedding. I wish you good luck, good health, and do you speak Espanol, as I understand? Yes.
Yes, I speak Spanish. Español.
Okay. In Espanol, te deseo amor, amor. I don't.
Okay.
Okay. Thank you all. Okay.
Thank you, Dulat. Jumat, any last word maybe to say something to the public or something? Jumat?
Okay, I'm sorry. Luis, of course, my congrats to you with your meeting, because as I totally to join the wishes from Dulat, and also I say you big love, Amur, and so on. And thank you very much, everyone, to our colleagues from different countries, Chile, Colombia, Venezuela, Brazil, Mexico, Great Britain, Kazakhstan. Yes, 7 countries today.
Yes.
Okay.
UK as well. UK.
UK, yes. I said Great Britain. Okay. 7 countries today joined. Different people from 7 countries. Just only in this meeting, and it's for me also big opportunity to meet with everyone, and I special thanks to Dulat, my colleague, for a very interesting speech today, and I just want to wish my very warm greetings to everyone. Thank you.
Okay, but please share the big funding from Kazakhstan, please, to the to our public. Don't forget that the second Latin American conference on superconductivity and magnetism will be held in Peru, Lima, Peru, at the University of San Marcos, from 23 to 28. I will give you the details.
Okay.
23 to 28 of October this year. A nuestro público que nos sigue, del 23 al 28 de octubre se realizará en Lima, en la Universidad Nacional Mayor de San Marcos, Facultad de Ciencias Físicas, la segunda conferencia latinoamericana en superconductividad y magnetismo. Los artículos serán publicados en la revista Journal of Superconductivity and Novel Magnetism de Springer. The articles will be published on Journal of Superconductivity and Novel Magnetism of Springer. Okay, now please everybody open their cameras. For more information about that, visit our web page of the LAFMAT. Okay. Bien, abran sus cámaras para decir chao a Dulat y a los amigos kazajos.
Hi, Dulat.
Hello.
Hi, Professor.
Hello, Mihail.
I don't know how to pronounce.
Ciao, Dulat.
Hi,
Ciao,
your
Dulat.
homes. Sergio.
Thank you.
Paulino, Luis, Mihail.
Ciao, José, Fermi.
My appreciation.
Bye. Ciao,
A
ciao.
gente se vê lá na praia. Boa viagem.
Sim.
Bye bye.
Goodbye.
Cortamos transmisión. Chao. Melvin,
Chao.
corta transmisión. Corta transmisión.